All right, we're going to turn our focus to integrals involving secant and tangent. I want to start with the fact that we have found the antiderivatives of sine and cosine, we knew those, and tangent and cotangent. Tangent and cotangent we know by the simple substitution, right? Tangent was sine over cosine, you remember? Tangent was sine over cosine, and we chose u to be cosine, and we got du is sine of x dx, and we got 1 over u, right? Remember that? So we got the antiderivative of tangent involving the log function. Well, what about secant x? Okay, well, that also involves a log function, but there's some magic that has to be done in order to do this. I say magic, it's something we probably wouldn't necessarily think of right away. First of all, take a look, if you will, about the derivatives of the secant function, right? That is what? Secant x, tangent x, and the derivative of the tangent function, if you remember, is secant squared x. So this is just a recall here, all right, from calculus 1. And so what I'm going to do is I'm going to do a little thing that might seem kind of strange. I'm going to rewrite this, what we're integrating, as an equivalent fraction. Essentially, I'm going to multiply by 1, and it's going to be, something divided by something. It's going to be kind of strange maybe at first, but I'm going to multiply top and bottom by secant x plus tangent x. Okay, this all is equal to what? 1. So I'm not multiplying by anything other than 1. Okay, and so when I do this, of course, this is secant x over 1. I'm going to distribute the secant x across the top, and so I'm going to get secant x times secant x is secant squared x, plus secant x times tangent x is secant x tangent x. Okay, over what? The denominator, 1 times secant x plus tangent x, just secant x plus tangent x. I am going to write that in a different order though. A plus b is the same as b plus a, right? So this is tangent x plus secant x. Now why did I write that in a different order? I guess I forgot my dx here. Okay, why did I write that in a different order? Well, take a look at the bottom, if you will, and look at the top, and look at these two derivative formulas. Do you see something? Do you see something? I hope you do. We have a simple substitution. If I choose u to be the denominator, what's my du? What's the derivative of tangent x? Secant squared x. Right? What's the derivative of secant x? Plus secant x tangent x. So all this, of course, is times dx, right? Du dx is secant squared x plus secant x tangent x, and that's exactly what we have in the numerator, right? So with this simply becomes the integral of 1 du. We'll just say du is secant squared x plus secant x tangent x dx over u, which the antiderivative is that, right? It's the log integral. And so we get the natural log absolute value of u, which is what? Tangent x plus secant x. Or secant x plus tangent x, doesn't matter the way we add those two together. In absolute value bars though, right? Plus c. There's the antiderivative. There's the antiderivative. Okay, so we now know sine and cosine antiderivatives, tangent and cotangent, and now secant, and I want you to show very similarly, I want you to show that the antiderivative of cosecant x is the natural log of cosecant x minus cotangent x plus c. I want you to show that. So think about how we did this one. Think about the derivatives of cosecant, which is what? Negative cosecant cotangent. Derivative of cotangent x is negative cosecant squared x, and see if you can figure out how to get to here. It's very similar to this. Multiplying by secant x plus tangent x, what do you think we're going to multiply by there? So think about that. Think about, you can almost see what you have to multiply by right here. So try and see if you can get that to work out. Okay, so now I want to look at a little bit more at secant and tangent in general. So we just proved this one for secant, and this was the one that we had for tangent by the simple substitution, right? Rewriting tangent as sine x over cosine x, we get this or this, right? We talked about that in a previous video. What about integrals involving powers of secant and tangent now together? Well, from the Pythagorean identity, we have, remember, 3 Pythagorean identities, if you recall. Right, we used this one for the sine and cosine integrals of this form, but we also have one involving tangent secant, of course, one involving cotangent cosecant. We're going to focus on this one now and make use of it here. So there it is again for us to remember. If the power of secant is even and positive, we're going to save a secant squared factor for the du, and we're going to let u be tangent x, because the derivative of tangent x is secant squared x. Okay, and when we do that, when we borrow that one secant squared factor, then all the remaining secants we can convert to tangents by the Pythagorean identity. Okay. If the power of tangent is odd and positive, we'll save a secant tangent factor. So product secant times tangent x, secant x times tangent x for the du, and then we'll let u be secant x. So if this is odd, I'll pull off a secant and tangent, meaning what's left over is even. I can convert that to secants again by the Pythagorean identity, and then we can integrate with respect to u equal secant x. Okay, so if secant is even positive, good news. If tangent is odd is positive, good news. Okay, bad news is what? Secant is odd and tangent is even. Then we're in a world of hurt. Okay, then we're in trouble. Okay, let's just focus on these cases. Notice here, tangent even, secant even. So since secant is even, we can use this first one. If the power of secant is even, we'll save a secant squared factor. Okay, so let's take a look at doing this one. So what we're going to do is rewrite this as tangent squared x, and then I'm going to peel off one secant squared x factor, leaving, of course, secant squared x. So that's going to be for the du, right? So in other words, I'm going to let u be actually tangent x. So my du is secant squared x dx. That's my du. Okay. Tangent squared x is u squared then, since tangent x is u. What about this secant squared x? Well, by the Pythagorean identity, what do we know? Secant squared x is what? Tangent squared x plus 1. Right, so this is indeed tangent squared x plus 1 from the Pythagorean identity, which is, in terms of u squared plus 1. See how everything is covered in terms of u, and so the u integral is what? Distributing through, right? This is u squared times u squared is u to the 4th. U squared times 1 is plus u squared. Du, secant squared x dx becomes our du, and now our antiderivative is easy. Very similar to the integrals we did involving powers of sines and cosines. Go back to u, which is tangent x, and we have our answer. All right. Beautiful, right? Very fun. Okay, so again, power of secant being even. Let's do another one. Okay. Again, power of secant is even, tangent is even, but if we have an even power, we can peel that off. So I'm going to do that. Peel one secant squared factor rather, which is going to leave this time secant to the 4th. Okay. So again, I'm going to let u be tangent x. So my du is secant squared x dx. All right. So that's got my du. Tangent to the 8th is now u to the 8th. And what about this? Okay, what about this? Well, remember we said that the Pythagorean identity was, just a reminder right here, Pythagorean identity is that tangent squared x plus 1 is secant squared x. So don't forget that. That's what we're making use of. So I'm going to replace this. This is going to be the same as secant squared, right? But secant squared is tangent squared x plus 1, right? So this becomes u squared plus 1, tangent squared x plus 1. Everyone see that? Okay, so, but it's u squared plus 1 squared, right? So this becomes the integral of u to the 8th, and u squared plus 1 squared is u to the 4th plus 2u squared plus 1. Right? So this is again u squared plus 1 squared. So I do have to expand that out. So, higher power, secant to the 6th, we would have u squared plus 1 cubed, and we'd have to, multiply that out, and it gets longer. So it does get a little bit longer, but we could do it, right? We could expand that out. Now I need to, again, distribute this u to the 8th through, and my integral becomes u to the 8 plus 4 is 12, 2u to the 10th, and u to the 8th. Antiderivative, easy. Plus RC. And go back to the original variable. U again was tangent x, and so here is our final result. As crazy as it looks. Okay, there it is, as crazy as it looks, right? So again, even powers of secant, we peel off a secant squared for the du, convert the remaining secants to tangents. Okay, now what if secant is not even? Okay, well, we better hope that tangent is odd, right? Because again, if tangent is odd, then we can pull off a secant and tangent factor for the du, and we'll let u be secant x. So the next example illustrates that. So notice here, secant is odd, so we can't peel off even power. You peel off a secant squared, but you'd be left with secant to the 5th. You can't convert all those secants over to tangents like we did up here. It has to be an even power in order to do that. You'd have a secant still floating around, and that won't work. But tangent is odd, and so I can peel off one tangent factor. So I'll leave tangent squared. One secant factor, I have secant to the 6th, and that will leave me a secant x tangent x dx. That will be for the du. So I'm going to let u be secant x in this case, and my du is secant x tangent x dx. So this right here is my du. Secant to the 6th is u to the 6th. And what is tangent squared x? So be careful here. Tangent squared x plus 1 is secant squared x. So tangent squared x is what? Secant squared x minus 1, right? So this is secant squared x minus 1, right? So this becomes u squared minus 1. There's everything covered. All right, so if our tangent factor is odd, we can peel off a tangent and a secant for the du, convert everything over to secants. So this becomes now, let's distribute this through that. It becomes u to the 2 plus 6, u to the 8th minus u to the 6th du. Again, easy integration here, just power rule. And then going back to the original variable, we have 1/9 u is secant x, secant to the 9th x minus have it. Okay, there we have it. So that's the idea behind tangents and secants. That's what I want you to be able to do. Now again, if there is an even power of tangent and an odd power of secant, then we've got a little trouble. Okay, so what I'm saying is there's a lot more to this than what we've shown you, but I want you to focus on the products involving sine and cosine, products involving tangent and secant. There is in the textbook a whole summary of integral forms involving trig functions, so-called table of trigonometric integrals. This is not exhaustive, but it does have some of the ones we looked at. If you remember in the last video, we derived this one essentially for sine squared x. I asked you to derive this one for cosine squared x, okay, using just a trig identity. These are the power reducing integral formulas for sine and cosine. Integral of tangent x, that's one we know. Here's a power reducing formula for tangent. Okay, we haven't actually used that one, but here it is. Cotangent, we proved that one. Power reducing formula for cotangent. Secant, well, let's see, you will prove the cotangent one. We proved secant, and hopefully you'll prove the cosecant. Power reducing formulas for secant and cosecant. So, and then there's actually a few more interesting ones involving products of sine or sine and cosine, where they're sine of and cosines of multiple angles, mx and nx, for instance. So, and this is just the tip of the iceberg. So there's lots of forms that we can use, and we'll later on look at using tables of integrals. But the point is, if you need an integral that you can't compute, you can use, like if you need to reduce high powers of secant, then you can make use of this, for instance. But the more important is how we got these. How did we get these? How did we get that secant integral? You remember that, right? And more importantly is the application of being able to evaluate integrals of the form products of sines and cosines, products of tangent and secant. That's going to be the important part. I want you to be able to use that technique that we've illustrated. Okay, we'll end here.